Okay, this video is about the concept of voltage. So to introduce that concept, I have a number of batteries here. Actually, some of these things are really cells. We're not going to draw any distinction between cells and batteries. We're going to use the terms interchangeably, okay? So maybe you have heard that something like this is a 9-volt battery, and what does that mean? Well, I have here a device called a multimeter, which is capable of measuring voltage. And if I take the two probes of this multimeter and I put them on the two ends of the battery, you can see the display there on the multimeter says 8.7 volts, which is pretty close to 9 volts. And I can do the same thing on this lantern battery. It says that this is a 6-volt battery, so let's see if that's true. We'll put the little probes on there, and it's reading about 6.3 volts, so that's pretty close. And these two guys, D cell, and it's reading about 1.4 volts, so that's pretty close to 1.5 volts. And here I have a AA cell, which is pretty close to 1.5 volts. When I make a good connection here, anyway. So the question is, what does it mean for this to have 6 volts and this to have 1.5 volts? Well, we're going to talk about that right now. In order to understand the concept of voltage, you have to understand the concept of electric circuits, okay? So I'm going to set up a simple electric circuit. This is maybe something that you've done back in middle school, where I have a lantern battery here, a 6-volt lantern battery, and I'm going to hook up a couple of wires to the two terminals of the battery. And then on the other ends of these wires, I'm going to put a light bulb. I'll clip a white light bulb on there. And you can see when I do that, the light bulb lights up. If I were to break a connection anywhere, the light bulb is going to turn off. So if I break the connection over here, the light bulb will turn off. So what's happening here is that electric charge is moving off of this little terminal of the battery, and it's going around through this little red wire, and then it passes through the light bulb, and then it passes out the other side of the light bulb through this black wire, and then it goes back into the battery, and then it doesn't just stop there, it actually continues through the battery to the other terminal, and comes out again round and round and round and round in a continuous movement of electric charge in a situation that we call an electric circuit. And if I were to break that circuit anywhere, that flow of electric charge would stop. Now, I should say that in physics, we always assume electric charge comes off the positive end of the battery and moves through the circuit toward the negative end of the battery. That is not the actual flow of electrons. Electrons actually flow in the opposite direction, but because of a rather unfortunate convention that Benjamin Franklin adopted hundreds of years ago, it kind of messed everything up for everybody. So it's rather confusing, but just remember that for physics purposes, electric current flows from positive to negative, even though the electrons are going in the opposite direction. Now, coming back to the concept of voltage, what does voltage mean? Well, it takes energy to run this light bulb. And so the charge that enters the positive side of the light bulb, that's this side of the light bulb, has to have some kind of electrical potential energy in order to run this light bulb. And when the charge passes through that light bulb, that electrical potential energy is turned into heat and light. So when the charge leaves that light bulb, it's back down to zero electrical potential energy. And what the battery does is it gives a boost of electrical potential energy to that charge. So basically the charge kind of limps into the negative side of the battery here, and then it gets a boost of electrical potential energy. And then when it comes out, it's very, very energetic electric charge, and then it loses all that energy. Actually, it converts all that energy into heat and light, and then it kind of limps back in to the negative terminal of the battery. Now, I should say that these little wires here have metal on the inside of them, so they're conductors. This circuit wouldn't work if I tried to, for instance, put a wooden pencil or something between the wire and the light bulb here, because the wooden pencil here is an insulator. So we have to have conductors to make the circuit work. Furthermore, this is not really true, but we're going to assume that as the electric charge moves through a conductor, it doesn't really lose any potential energy. It converts all of the potential energy into, in this case, heat and light when it kind of moves through the light bulb. But it doesn't lose or gain any energy as it's moving through the actual wires. So over here we get sort of an energy boost, and here we convert energy, electrical energy, into some other form. This situation is not unlike this little model here I have. So here's my little model here, and if I turn it on, these little penguins go up to the top of the track here, and then they go all the way down to the bottom, and then at the bottom here they're elevated back to the top of the track. This is similar to the electric circuit with the light bulb, where this little stairway is elevating the penguin's potential energy. That's like the battery. And the penguins themselves are like the electric charge that's flowing through the circuit, and the circuit itself is the little track. So very much like an electric circuit. Okay, the definition of voltage is V for voltage is equal to delta U electrical divided by delta Q. So you can think of this as being the voltage of a battery. This is being the change in electric potential energy that charge will get as it moves through the battery, and this is equal to that amount of charge that moves through the battery. Might be a little bit easier to understand this equation if we kind of rearrange it and write it this way. Where this is equal to the change in electric potential energy, and the operative word here is energy, and that's going to be in joules, symbol J, like any other kind of potential energy. This is going to be sort of a quantity of electric charge, and that's going to be in coulombs. And then finally, that V here is going to be voltage, which is the same thing as electric potential difference. Now, electric potential difference looks a lot like electric potential energy, but they're two different quantities. Delta U is different than V. So if it ends in energy, they're talking about delta U. If it's just electric potential but doesn't have an energy on it, then we're talking about voltage or electric potential difference. And electric potential difference or voltage is measured in joules per coulomb. So contrast that with electric potential energy, which is just joules. And that's the same thing as J over C. And we also have a special word for a joule per coulomb. We call a joule per coulomb is a volt, okay, or symbol capital V. So we have a capital V here that's the symbol for the unit of volt, but it's also the symbol for the quantity of voltage, okay? So you can think of this as being the amount of electric potential energy that a certain quantity of charge will get as it moves through a battery with voltage V. So, as an example, let's say we have 2 coulombs of charge, moves through a 6-volt battery. And what we want to know is what electrical potential energy, remember the operative word here is energy, will the charge have as it leaves the battery. So that's going to be my question here. And it's pretty easy to solve using this equation. Delta U electrical, remember that's a joule thing, is going to be equal to that quantity of charge, which is 2 coulombs in this case, times the voltage of the battery, which in this case is 6 volts. And that's equal to 12, kind of weird unit, Coulomb volts. But we can make it into a more normal unit by realizing that this is the same thing as 12 coulombs times a volt, which is a joule per coulomb. And the coulombs cancel out. And that leaves us sort of our normal unit of potential energy, which is joules, 12 joules in this case. Now there's another quantity we need to be familiar with, and that quantity is called electric current. And electric current has the symbol I. And what electric current is it's the amount of coulombs per second that pass through a certain part of an electric circuit. So when I showed you the circuit with the light bulb, the number of coulombs per second of electric charge that pass through the light bulb would be the electric current. So we can define electric current as being delta Q divided by delta T, where this represents the amount of charge that is passing by a given point, and this represents the time it takes that charge to pass that point. So this is coulombs and this is seconds. So the units are going to be coulombs per second. But we have a special name for a coulomb per second. We call it an amp or amps. So 1 amp of current, of electric current, is 1 coulomb per second of electric current. Now, we can actually combine the formula for electric current with the formula for voltage and get a formula for electric power. Okay? So this is how we do this. It turns out that electric power, so P electric, which remember is a watt thing, right? Power is a watt thing. Turns out it's equal to voltage times current, or electric potential difference times current. And to see that, we recall that voltage is basically delta U electric, which is electric potential energy difference, divided by delta Q. And so that's my voltage. And from up here, my current is delta Q divided by delta T. And notice the delta Q's cancel out. And I'm left with change in electric potential energy divided by delta T. Well, the electric potential energy is getting changed inside a battery, for example, because the battery is doing work on that electric charge. So we can also call this work electrical divided by delta T, and that's basically the definition of power. Work over time. And so we can get the power of a system, of electrical system in watts, by multiplying voltage by current. So I, for instance, could get the power that this light bulb requires by taking my little voltmeter and measuring the voltage across that light bulb and multiplying that by the current going through the light bulb, and that'll tell me sort of the power consumption of the light bulb in watts. Now, there's another electrical component that we need to be familiar with, besides light bulbs and batteries, and that is this thing here. This is called a resistor. And the purpose of a resistor is to resist electric current, to kind of slow the electric current down or reduce the electric current. Now, why in the heck would we ever want to do that? Well, there are some devices, like this little LED, for example, that if you hook it directly up to a battery, too much current will run through it and it will burn out. So let's just kind of do that just for the fun of it. Let's take couple of these little leads here, hook it up to our battery, 6-volt battery, 6 joule per coulomb battery, and we'll take our light bulb here, or actually not light bulb, but LED. And this is supposed to be a green LED. It's supposed to light up green, but when I hook it up, it's basically lighting up orange, and now it's turning red. I don't know if you can see it through the color camera, but it's burning way, way, way too bright. Now it's starting to turn very red, and now it's just completely burned out. Okay, well, I guess there's still a little life left in it. But basically, in fact, it's even starting to melt on the side here, okay? So we put way, way too much current into this LED. And if we want to actually hook up an LED in a circuit, we have to kind of turn the current down so it doesn't burn out the LED. So now I want to create an LED circuit here that's got a resistor in it to limit the current. So again, a reminder how this works. Charge is coming out from the positive end of the battery. It's going through the LED, and it's coming out over here. And the LED isn't lagging because there's a break in the circuit here. But when I connect those two, the current will go back into the battery. Now I don't want to connect them directly because they'll burn out the LED like I did before. Instead, I want to make the current go through this resistor, which is kind of slow down the current. And when I do that, I don't know if you can see it, but the color of it, but now I have my LED lighting, but it's not turning orange or red, and it's not smoking and melting and doing the things that it did before. And that's because I've slowed down the current. I've reduced the number of amps going through the LED. Now, something else is happening in this circuit too. Before, when I had a light bulb in there, just an ordinary light bulb like this, all of the potential energy was being turned into light and heat when the current went through the light bulb. But here we have sort of two steps. Some of the potential energy is being converted into light and heat in the LED, and then the rest of the potential energy that the charge has is being basically converted into heat in this resistor. So that by the time it goes through the resistor, now we're back to zero energy. Okay, so the energy is lost in two stages here, or I should say transformed in two stages. From the when it goes across or goes through the LED, and when it goes through the resistor. Now you may say to yourself, well, wait a minute, aren't we losing electrical potential energy and that we could otherwise be more usefully employed by having the current go through this resistor and having being converted into heat? And the answer is yes. We are basically wasting electrical energy by having this resistor in there, but we need to have it in there, otherwise we would burn up the LED. There's a reason, for instance, why your computers have fans in them. The fans are to extract all the waste heat by all the resistors inside the computer circuit. That heat is, that energy, electrical energy, is basically being wasted by being converted into heat, but that's sort of the cost of doing business. Anytime you have any kind of useful electric circuit, you're probably going to be generating a certain amount of wasted heat. Now, just for the fun of it, let's actually figure out how much energy we're consuming, or how much power is required to run this LED, and how much power is basically being converted into heat inside this resistor. Now, to do that, I need to bring my multimeter back here, but this time I want to have it hooked up to measure current, okay? In addition to measuring voltage. But the voltage I can actually measure right now, so let's do that really quickly. I'm going to reset this thing and get it to measure here. And I'm just going to put the meter, let's say right about here. And then I'm going to take my two probes, and I'm going to measure the voltage across the LED and then across the resistor here. So across the LED, I'm getting about 2.3 volts. So let's write that down here, 2.3 volts. And now let's see what I'm getting across the resistor here. So I move it across the resistor. And now this is going to be about 3.7 volts. And notice that 3.7 volts and 2.3 volts add up to the 6 volts that the battery is boosting that charge. Okay? And that's always going to happen. I get 6 volts of boost, and I get a total sort of drop in voltage of 6 volts as well. And we're going to look at that situation more later. But these two drops should add up to the boost that the battery is giving that charge. Now I'm going to go ahead and measure the current going through the circuit. And to do that, I need to actually break the circuit here. So notice the LED goes off. And what I'm going to do is I'm going to take my two leads, and now I've got this thing set up to actually measure electric current. It actually measures electric current in milliamps as opposed to amps. So we'll have to do a little conversion there from milliamps to amps. But I'm going to take my two probes, and I'm going to take one of them, I'm going to hook it up to one of the alligator clips that goes to the battery here. And then the other one, I'm just going to, after I broke the circuit here, I'm going to put the other one on the resistor. Notice the LED lights again, because now I've completed the circuit. It's just that now the current is also going through the meter here, the multimeter, and it's reading 36.2 milliamps. So let me write that down. I is equal to 36.2 milliamps. That's the symbol for milliamps. Let me just verify that one more time. Yeah, 36.2. Now you may ask yourself, well, wait a minute. That's just for the part of the circuit where I inserted the meter, but it's for every part of the circuit. The amount of current running through any part of this circuit is going to be the same. It's what's called a series circuit, and in a series circuit, the current's the same everywhere. So just to prove that, I'm going to break the circuit in another part of it right here, and I'm going to now put my meter in there. I'm just going to kind of hold that on there like that. And it's also reading 36.2 milliamps, okay? Even though I'm now measuring it in a different part of the circuit. So now that I have the milliamps, now I can actually compute the power. Now remember, this was the LED here, and this was the resistor over here. And 36.2 milliamps is the same thing as 0.0362 amps, because 1,000 milliamps equals 1 amp. So I move the decimal point 3 times, 1, 2, 3, to get the amps. And so let's measure the power of the LED, how much power the LED is consuming. It's the voltage across the LED times the current going through the LED. And that's going to be 2.3 volts times 0.0362 amps. And when I do that on my calculator here, 2.3 times 0.0362, I get about 0.083 watts. You can compare that to a 100 watt light bulb. It's much lower than a 100 watt light bulb, only 0.083 watts. Okay? Now let's look at the power for the resistor, how much power the resistor is consuming. It's going to be V across the resistor times the current going through the resistor. Well, the voltage across the resistor was 3.7 volts. Remember that these two voltages have to add up to the voltage boost of 6 volts that the battery gives the charge. The current is going to be the same. In a series circuit, the current is the same everywhere. Okay? So if I multiply these two together, 3.7 times 0.0362, what I get is 0.134 watts. Okay? So I'm actually, the resistor, which does nothing other than keep the LED from burning out, is actually consuming more power than the LED itself. Again, that's sometimes the way things work out. Our appliances are not always that energy efficient, and the cost of doing business in our modern electronic age is to waste a certain amount of our electrical power as sort of useless heat that our electric circuits generate. So just a quick recap. Voltage is joules per coulomb. Batteries have a voltage because for every coulomb of charge that goes through the battery, the electric potential energy of that charge is boosted by an amount equal to its voltage times the amount of charge moving through it. Things like resistors and light bulbs and LEDs will consume electric power, and therefore there will be voltage drops across those devices. The voltage drops are going to add up to the voltage boost of the battery.